Hello and welcome. Section 3.1, we work on linear models. So basically we're going to combine the work we did in section 1.3 on how to set up the differential equations with our work in chapter 2 on how to solve them. So we'll start with a growth and decay model. So we have some substance that decays at a rate proportional to the amount present. This is at t greater than 0. The half-life of whatever mystery substance we have is 10 years. So we're going to find out how long it will take for 85% of the substance to decay. So we start by doing our 3.1 work on this, setting up the differential equation. So the change in the amount of the substance with respect to time is proportional to equals k times the amount of the substance. So then we solve our differential equation. So this part was in 1.3. The second part we learn how to do in chapter 2. So this is linear, no surprise, it's in the linear section. So dA dt minus Ka is worth 0. So then we can just find an integrating factor. E to the integral of minus k dt is e to the minus k times t. So we multiply all three terms by our integrating factor, and we have e to the minus kt times dA dt minus ke to the minus kt times a. It's worth 0 times anything. That one's going to drop to 0 anyway. So our left side, hopefully you recognize as a product rule happening. Derivative of a, keep the other factor, keep the a, differentiate the e to the minus kt, which would be the minus ke to the minus kt. So we have the derivative of e to the minus kt times a. Right-hand side is 0. And then we integrate both sides with respect to the variable t. As per usual, I didn't leave myself quite enough room to squeeze my dt in there. So we have antiderivative of a derivative. We're kind of running in circles there. We're back where we started. We have the e to the minus kta. Antiderivative of 0 is just some constant. So the derivative of any constant would give you a 0. Now, typically we would want to get the a by itself, so we'll multiply both sides by e to the kt. So then a is ce to the k times t. And a of 0 is just a naught. And on this one, they didn't give us an initial amount, so we'll just call that a naught. But that is enough to let us find c. So a naught is c e to the k times 0. K times 0 is 0, e to the 0 is a 1, so a naught is c times 1, so c is a naught. So now we can say our equation is a is equal to a naught e to the k times t. So we just kind of keep building it piece by piece using all of the information that they gave us. So they gave us the half-life and an amount of years. So remember, half-life is referring to how long it takes until you have half of the original material remaining. So the original material is a naught. So then the new amount would be 1/2 of a naught. It's a naught e to the k we don't know yet, and t was given as 10 in years. So the a naughts cancel, so half is e to the 10k. We can solve this thing for k. So natural log of a half is worth 10 times k. Natural log of a half and negative natural log, or negative natural log of 2 would be the same thing. Since quotient turns into, let's just do that real quick on the side just as a reminder, because I do have a tendency to do that sometimes. ln natural log 1 over 2. Log of a quotient is the difference of logs, so that would be natural log of 1 minus natural log of 2. Natural log of 1, though, remember, is 0. So you'll sometimes see this as negative natural log of 2. That's the same as natural log of a half. So you will see it written both ways. I just wanted to make sure you're okay seeing both ways. So k is opposite of natural log of 2 divided by 10. So now we can add a little bit more detail to our equation. Now we can say that the amount is initial amount times e to the negative natural log 2 over 10 times t. It's a little hard to read there. That is a natural log there in front of the 2. All right, so moving on, we put some more detail in there. So the next bit of information they give us, they want 85% of it to be decayed. So that means that we have 15% left. Since there was 100% total. So you're just using a complement. So then 15% of the original is remaining. So the original, remember we said, was a naught. So 15% of a naught, 0.15 a naught, is worth a naught e to the negative natural log 2 over 10 times t. So once again, the a naughts will cancel. So whether we started with a gram of this or a metric ton of this, it's all decaying at the same rate anyway. So it doesn't matter what the initial amount was. It'll take the same amount of time to have 85% of the 1 gram decay away is 85% of a truckload. All right, so we have a variable and an exponent, base e, so we'll do natural log both sides. So natural log of 15/100 is worth negative natural log 2 divided by 10 times t. So then we just multiply by the reciprocal there. So then t is negative 10 natural log of 15/100 divided by natural log 2. And for just a regular problem, I would just keep it there and slap years on that. That it's a word problem, even most math people like me would say, okay, well, approximately what is that in years? So this is approximately 27.37 years. And that should fit with what we know of it. If we start out with 100% of it, and it has a half-life of 10 years, so 10 years down the road we have 50% of it. Then we lose half of that 50%, so now we're down to 25% of it remaining after 20 years. Let another 10 years go down the line, and we're at half of the 25%, so 12.5% would be left after 30 years. So 15% left after 27.37 years. That does fit reasonably well with what we would expect. And population growth models, remember, work the same way as decay models would work. All right, so our next one, we'll take a look at Newton's law of warming and cooling. All right, so change in temperature. Of an object is proportional to the difference in temp between the object and ambient temp. Ambient temp, remember, is T sub m. So any of these heating and cooling problems, we can start with the same differential equation. So change in temperature, so we'll use cap T for temperature. With respect to time, we use lowercase t for time. So if you're one of the people that tends to use upper and lowercase interchangeably, please don't do so in this problem. You will get very lost, and I will get very lost grading it. Is proportional to equals k times difference in between the temperature of the object and the ambient temperature. All right, so we can use this in many different applications. So we'll do kind of a crime scene investigating type of application. So do a body found in a 72-degree Fahrenheit room. We're going to assume that it's a constant temp. Time of initial examination. Body temperature was 75 degrees Fahrenheit. 1 hour later, body temp was 74 degrees Fahrenheit. So we'll make another simplifying assumption. So one of them being that the temperature of the room was constant, not sort of what really kind of happens in most homes. The temperature kind of rises and falls. Ovens work the same way. It doesn't have a way to keep it constantly at precisely that temperature, so the heat source kind of kicks on and off. We'll make the simplifying assumption of a constant heat outside. We're also going to assume 98.6 degrees Fahrenheit body temp at time of death. So we want to know how long was it between the death and the initial exam. How long until the body was found, basically. All right, so we already have some information that we can throw into the differential equation. The ambient temperature of the room was 72 degrees Fahrenheit. So change in temperature with respect to time. We don't know K yet. Don't know T, but we do know T sub M, ambient temp, to be 72. So we can solve this differential equation. So we'll do a little distributing, and change in temp with respect to time is KT minus 72K. And set it up as a linear, so we'll just move the KT. So change in temp with respect to time is, minus K times temp is negative 72 times K. So then we'll do our integrating factor, e to the integral of minus k d little t. So that's e to the minus k little t. So just like last time, everyone's hit with e to the minus k little t. So e to the minus k little t dt d little t minus k e to the minus kt times big T is worth negative 72 k e to the negative k little t. All right, so left-hand side is once again a derivative with respect to time. So this was the derivative of e to the negative kt times big T. So product rule. Differentiate the t, keep the e to the negative kt, then trade. Keep the t, differentiate e to the negative kt. And we'll hang on to that right-hand side for the moment. So then we integrate. So left side is e to the minus kt times big T. Right-hand side, I'll hang on to that negative 72k for the moment and integrate e to the negative kt. Well, we know we have e to the negative kt involved. We've already taken care of this much of the constant. If I differentiate this right now, I would get negative k e to the negative kt. So I will need a negative 1 over k there as well. And we'll add arbitrary constant c. The negative by negative will drop off, and the k over k will drop off. So we have e to the negative k little t big T is worth 72 e to the negative kt plus arbitrary constant c. All right, so next up, we want to get that temp by itself. So temp is worth, we'll multiply everything through by e to the positive kt, which drops that 72 to being by its lonesome. And then we have plus ce to the k times t power. All right, that's about all I'm going to fit onto that page. But before we flip, one little fact that we know, 98.6 at the time of death is t little t equals 0. So we'll put those two facts to work in this equation on the other side. So we had, recall, T equals 72 plus C e to the kt. So the temperature, 98 and 6/10 is worth 72 plus C e to the k times 0. K times 0 is 0, e to the 0 is a 1. So basically that term becomes a 1. 1 times C is just C. So 98.6 is 72 plus C. So then C is worth, that would be 26.6. So now we have C in hand. Now we can add a little bit more detail to our equation. We know temperature is going to be 72 plus 26.6 e to the k times t. So we're down to 3 variables from 4. We're getting better. Next order of business is to figure out what k is. So 2 facts that we had, we knew that at t sub 1 greater than 0, temp was 75. And we also know that at 1 hour later, so T1 plus 1, if T1 is greater than 0, T1 plus 1 we already know is greater than 0. Temperature was then 74 degrees Fahrenheit. So if I plug those 2 facts in one at a time, so the first one, 75 is equal to 72 plus 26 and 6/10 e to the k times t sub 1. So just time 1. We don't know what time 1 is yet. That's what we're after. We can do a little bit of cleanup on that. We can say 3 is 26.6 e to the k t1, or e to the k t1 is 3 over 26.6. So I'm going to put a little 1 by that guy. We'll come back to him. Plugging in the second bit of information, that an hour later the temp ended up at 74. So 74 is equal to 72 plus 26 and 6/10 times e to the k times, now our time is t sub 1 plus 1, 2 terms, so make sure you throw those guys in parentheses. So a little bit of cleanup on this. We can of course move the 72, so 2 is worth 26 and 6/10 e to the, we have k t sub 1 plus k. So if I'm adding exponents, that must have meant I was multiplying with the same base. So let me go ahead and show that. So 2 is 26 and 6/10 e to the k t1 e to the k. So multiplying with the same base, my shortcut would be to keep the base, add the exponents together. So these are just 2 different ways to write the same thing. What I want to do though is I want to make it look like equation 1. I want it to look like e to the k t1. So that means I want to move this 26.6 and the e to the k. So we have 2 over 26.6 e to the k is downstairs, is worth e to the k times t sub 1. So each one of these, I'll put a little 2 by that guy. Each one of these e to the k t sub 1s must have the same value, so these 2 must equal one another. So then 3 over 26.6 has to have the same value as 2 over 26.6 e to the k. So the 26.6's and the denominators cancel. We'll multiply both sides by 26.6, and we get 3e to the k is worth 2. So e to the k is 2/3. So then k would be the natural log of 2/3. So now I can add a little bit more detail again to our equation. So t is worth 72 plus 26 6/10 e to the natural log of 2/3 times t. Now what we can do is plug this information back in here. Now that we have everything but a time and a temp, we can plug in this temp and find this time. So then 75 is worth 72 plus 26 6/10 e to the natural log of 2/3 times whatever t sub 1 is. So that's our goal. So we have, actually we could even have kind of picked it up here. So our work, we get our e to the natural log of 2/3 times t is worth 3 over 26 6/10. So just move the 72, divide by the 26 6/10. So then we'll take the natural log of both sides. That way we rescue this exponent from the e and make it into just the natural log of 2/3 times t instead of something raised to that power. But then we do have natural log of 3 over 26 6/10 on the other side. These are t sub 1's. So then t sub 1, natural log of 3 over 26 6/10 over natural log of 2/3. And again, since we want an amount of time for a story problem, a word problem, a little approximation on that wouldn't hurt. So natural log of 3 over 26 6/10, close it up, divide by natural log of 2 over 3, close that guy up. So t sub 1, approximately 5.38 hours. So about 5.38 hours, 5.4 hours between the time of death and the time of the first examination. So they can give a reasonable estimate of when they think this person passed away. So that's a little of the CSI type stuff. So the next one, we get to play with our friend mixtures. So the idea in the mixture is we're pumping things in and out, and the change in the amount of the substance we're mixing in with respect to time, rate in minus rate out. All right, so here's what we know. A tank with 600 gallons of water is 40 pounds of, what did I pick, salt mixed in. So I took a 40-pound bag, dump it into the 600 gallons, mix it up. There we have what's sitting in the tank before I turn the pumps on. All right, what we're mixing in. Mixture containing 3 pounds salt per gallon of water, is pumped in at 2 gallons a minute. Tank is mixed. So we're assuming we're constantly mixing this stuff together, that it's well mixed, that we don't have one high concentration just sort of shooting in and out very fast. We mix it in there, and then the other pump is way down at the other end after it's well mixed. Tank is mixed, and the solution is pumped out at 3 gallons per minute. So what is the amount of salt at time t? So change in the amount, rate in minus rate out. So rate in, the simpler of the two, we'll do that one first. So inbound, mixture in, we have 3 pounds per gallon, and we're pumping in 2 gallons per minute. So 6 pounds per minute is coming in. So the out is a little more complicated. One thing you might notice is that our rates for the pump in and pump out are not the same. It's going in at 2 gallons a minute and out at 3 gallons a minute. We're losing volume in this thing. So we need to find the number of gallons with respect to time. So it's going in at 2 gallons a minute, out at 3 gallons a minute. So we're losing 1 gallon a minute. So then the number of gallons with respect to time be the initial number of gallons minus 1 times t, or just t. So we're assuming t is at least 0. We can say greater than or equal to 0. We don't really have any action happening at time t equals 0. We're just turning on the pumps. Nothing's changed yet. At that time, we know 600 gallons, 40 pounds of salt. Anything after that, we'd have to do the diff EQ thing. All right, so that's enough information to find our rate out. We have 8 pounds of salt out of 600 minus t gallons, and it's going out at a rate of 3 gallons per minute. So we have 3a over 600 minus t is our rate out in pounds per minute. So then change in the amount with respect to time, rate in minus rate out. Rate in 6 minus rate out, 3a over 600 minus t. All right, so I'll make this look like the sort of standard linear differential equation, dA dt plus 3a over 600 minus t is worth positive 6. So we'll pick it up there on the other side. where we'll work with our integrating factor.